and I will upload this recording onto my YouTube channel tonight before I go to sleep. Okay, all right, so let's get started. So what chapter do we want to start with? 16, okay. So, okay, I need a fizzy drink to get through this. All right, so let's start on chapter 16. A specific question number? 16. Okay, we'll just start with number 9. So the fun thing about this midterm, it is all based upon big K. Remember midterm 1, we talked about a different K, rate constant, that was small k. Now we're talking about big K. Big K is different, but still related to rate constant. And we'll talk about its significance here. Okay, so chapter 15, 16, and 17, all based upon chemical equilibria, which is big K. So let's just go through these questions, and then if someone feels an urge for a certain question, we'll do that one. All right, so based on these particle diagrams of various acids. So chapter 16 is about chemical equilibria. It's just specifically about acid-base equilibria. Oh yeah, just tell me, just say it. Tell me. Okay. All right. Got it. There we go. All right. Yes. So chapter 16 is just specifically based upon acid-base equilibria. So it's still chemical equilibria where K is comprised of concentration of products over reactants. It's just a special case here where we have acids that typically donate H+, bases typically donate OH-. So let's look at these particle diagrams. Let's identify them as weak acids or strong acids. So finally, we're expanding on our acid definitions from 1210. Remember, we just had you memorize the 7 strong acids and everything else was weak. Well, now we're really diving in deeply into that. So of these, let's remember our ideas of strong acids. It's the same definition of strong electrolytes. So which one of these is a strong electrolyte? HX, HY, or HZ? What do we think? The second one, yeah. So this is the only one that is a strong acid. The other two, HX and HZ, these two are weak. Great. So of these 3, which one have K values? Or do all of them have K values? Which ones actually undergo chemical equilibria, therefore have a K? Do all of them have K values? No. Which one does not have a K value? The HY, the strong one, because the idea here is with a strong acid, you know, we take HY and it completely dissociates into H+ and Y-. So when this dissociates, all we have is product. So if you think about, you know, what K is products over reactants. In this picture, there is no reactants. All right, and so, you know, if you tried to make a K value, there would be a 0 in the denominator. Are you allowed to put a 0 in a denominator? No, you're not. So that's why a strong acid doesn't have a K value, but the 2 weak ones do. So of these, which one ionizes the least? HX or HY or HZ? So we can right off the bat eliminate that middle one because strong acids, you know, ionize the most. All right, that it's completely ionized actually. So we're just looking at the 2 weak components here. So the acid that ionizes the least, we're looking at the ones that makes the least amount of ions. So basically the least amount of products. All right, so if we just look at this, you know, generic chemical equation I wrote here, basically we're looking for what picture has the least amount of products in the picture. So if I look at these, you know, HX I think only ionizes 2 molecules versus HZ ionizes 1, 2, 3 of them. So hopefully you can see that HX is the one that ionizes the least because it has the least amount of ions present, the least amount of products. Okay. So which acid has the smallest Ka value? What does that mean? What does that mean? The one that's the weakest acid? Yeah, the one that's the weakest acid. So the one that is the weakest acid, does that donate a lot of H+ or not a lot of H+? Not a lot of H+. So really, B and C are actually the same question. See how they're the same question, that these two ideas are very similar. Something with a small Ka value is also going to ionize less, because the idea of what Ka is H plus, times X concentration over HA. So basically, if something ionizes a lot, you're going to have a really big numerator. So Ka will be large, but this question's asking for the least. All right, so those are the acids. So what substance is going to behave as the strongest base? So note here, I don't have HX, HY, HZ. I have NaX, NAY, NaZ. What are these? Are these acids? No, these are their conjugate bases. So what is the typical strategy here? Relationship, how, depending on the strength of our acid HX, all right, okay, as the acidity strength of your acid increases, if you look at the basicity of your base, it typically decreases. So based upon this question, it's essentially asking which acid is the weakest acid, because it's looking for the strongest base, so the answer will be NaX. So essentially the answer I'm looking for is the weakest acid, HA, will have the strongest conjugate base, A minus in this case. All right, so that's how that relationship is there. All right, and so that's pictorially how we can look at it. All right, and you could even calculate. You could do a back of the envelope calculation for the K values here, and you should be able to get the same thing. That the Ka for the weak acid HX will be smaller than HC. All right, so the question. Okay, so 2 people said 25. All right, so let's do 25. Or no, I don't want to do that. Let's do 10. Let's do 10. All right, because I get a lot of questions about Arrhenius acids, Bronsted-Lowry acids, Lewis acids, and what all of that means. They're basically just different categorizations for assigning acids and bases. And this is a really important concept, because you'll come back to this idea in organic chemistry. How many people are going to take organic chemistry? Yeah, I'm assuming all of you. All right, so this is a very important concept, understanding, okay, weaker the acid, stronger the conjugate base. If you keep that in your back pocket for organic, that will take you very far. For me, when I took organic, I did not keep that in my back pocket, and I paid for it. All right, so keep that up here. All right, so in terms of assigning acids and bases, we had 3 different types that we talked about. We talked about Arrhenius acids and bases, Bronsted-Lowry, and Lewis acids and bases. So as we talk about these 3 different systems, they essentially get broader and broader and broader. So an Arrhenius acid, this is typically what we think of. Arrhenius acids, we just define as like acids increase the amount of H plus in solution, while bases increase the amount of OH minus in solution, all right? But sometimes those definitions don't include everything. So with Bronsted-Lowry acids and bases, we typically were a little bit more generic, and we say, okay, with a Bronsted acid, this is an H plus donor. It will donate an H plus, while a Bronsted-Lowry base is an H plus acceptor, right? So the idea here is that an Arrhenius acid is also a Bronsted-Lowry acid, most likely. A Arrhenius base is most likely a Bronsted-Lowry base as well. You're not going to find something that is an Arrhenius base and a Bronsted-Lowry acid. You're not going to see that mixed up. It's just a different, I guess, focus. Here with Bronsted-Lowry acids and bases, we're looking at H pluses moving around in a reaction. And this is different, and it contrasts to Lewis acids and bases, because we're not focusing on the proton. What are we focusing on in our Lewis definitions? Electrons, yes. So instead of hydrogen, a proton moving around, we're focusing, okay, Lewis acids, they are electron, what are they? Acceptors. Right? And I like to remember this, H plus is literally just a proton. It doesn't have any electrons. So an H plus has to be a Lewis acid. It has to be an electron acceptor because protons can't donate any protons. They can only accept protons. So this definition just kind of expands even more. Arrhenius acids are most likely Bronsted-Lowry acids, which are most likely Lewis acids also. So do you see how the definition just gets broader and broader and broader, right? And then finally, what do you think a Lewis base does? It's not an electron acceptor, it's a electron donor. Yes, yes, electron donor. Okay, all right, so let's look at this reaction. Identify the Bronsted-Lowry acid and base for the forward reaction. So it says Bronsted-Lowry, so what should our focus be? Protons, yes, protons, which also means it's the same thing as an H plus. We want to focus on, okay, where is that H plus moving from reactants to products? So if I look at this, you know, and kind of track, where is this hydrogen going? This proton is, I guess, moving from this HCl to the NH3. So I'll track, so here, I'll just draw in green here, that hydrogen is moving to this reactant, and that's why now this nitrogen has 4 hydrogen bonds to it, and then that chloride is all alone there. So based upon how this movement, how this proton movement is happening in the forward direction, HCl is what? The what? Acid or base? It is the acid because, so Bronsted-Lowry acid, I'll be super specific here, because it is donating an H+. It's donating an H+, and then what is accepting the H+? Ammonia. Ammonia is accepting the H+, so this is our Bronsted-Lowry base. Perfect. All right, so let's do the same thing in the reverse reaction. Right, so the reverse reaction, start on the product side and think, okay, how can I turn the products into the reactants? Where is that hydrogen going? The hydrogen is popping back off of that ammonium, NH4, and it's sticking back onto that chloride. All right, so in this example, if we're looking at the reverse reaction, okay, so the reverse reaction here, what is our acid now? What is our Bronsted-Lowry acid now? It's which one? And NH4 is our Bronsted-Lowry acid. Yes, Bronsted-Lowry acid, and then chloride minus, this is gonna be our Bronsted-Lowry base. Perfect. We're focusing on where the H plus is moving. Okay, so we talked about Bronsted-Lowry. What do you think we're gonna talk about next? Lewis, yes. Oh, it's the same reaction. Huh, interesting. But again, now our focus is on electrons. Electrons, okay. So we know that the hydrogen is, you know, popping off of that HCl and attaching itself to the nitrogen on ammonia. But let's think about it differently, because this is a Lewis acid, we're thinking about electrons moving. A covalent bond is composed of what? 2 electrons. So Lewis acid base theory says, oh, these 2 electrons that are in the lone pair of ammonia grab a hydrogen off of HCl, and then these 2 electrons that are on that covalent bond between HCl go on to chloride. Do you see where the electrons are moving now? So this arrow that I drew, see this arrow I drew? That is now the new covalent bond on this side, on the product side of the reaction. Right? See those two, that lone pair just became a covalent bond. You see it? Okay, so now using Lewis acid base definitions, a Lewis acid is what? An electron, what? Acceptor. So based upon this picture, the blue arrow is the movement of electrons. What is accepting the electrons? Ammonia. Someone said, what is accepting the electrons? The hydrogen in the HCl. So this is my Lewis acid. Oh, now what is my Lewis base? Ammonia, because the lone pair is on ammonia. So this is my Lewis base. Because ammonia, the lone pair on ammonia is donating those electrons. Okay, all right. Does the acid base definition, did it change at all? Did it change at all from up here? No, it's still ammonia's a base, HCl is an acid. In this definition, Lewis acid-base theory, ammonia is still the base, HCl is still the acid, it's just our focus is different. And if you just remind yourself that a lone pair it can be, two electrons can be a lone pair, or it can be a covalent bond between two atoms, that'll get you pretty far. All right, so let's do the reverse reaction. But I bet you can predict it as well. All right, so remember chloride here. Chloride, when you think about, you know, how many valence electrons it has, right? It actually has eight electrons around it because it has like a full octet. All right, there's a lot of electrons on there, right? So let's look at the reverse reaction. We know that hydrogen needs to pop off and reattach itself to chloride. So think about, focus on the electrons. How is that going to happen in terms of electron movement? One of the lone pairs on chloride is going to grab that hydrogen, that proton, and then the two electrons that are in that covalent bond are going to attach itself to nitrogen. All right. Okay, so now where the arrows are moving, the arrows are showing where the electrons are moving. Chloride would be what? Is it accepting or donating electrons? It's donating. So if it's donating electrons, what is it? It's a base, so it's a Lewis base. So the nitrogen is doing what? It is accepting the electrons. That's what you see, that little arrow right there, all right? It's taking the two electrons from the covalent bond and you're shoving it on nitrogen. Ammonium here is the Lewis acid because it is accepting electrons. Is this definition any different than our Bronsted-Lowry definitions? No. Ammonium is still the acid and chloride is still the base. It's just, again, we're just refocusing on electrons rather than hydrogens moving. All right, so those definitions, they match each other. You're never gonna have a mix match of like a Bronsted-Lowry acid and a Lewis base. That's probably not going to happen, all right? But there's something special about water, right? Water, okay, H2O, it looks like this. H2O has two lone pairs, right? Water is special in that it can donate electrons, so it can be a base in this case, or it can be an acid and donate one of those hydrogens as well to make a hydroxide. So water is amphiteric in that sense, where it can behave as an acid or a base depending on the strength of stuff it's reacting with. All right, okay, all right, so that's 10. I wanted to do 10. Okay, when in doubt, when we are asked to compare between Arrhenius, Bronsted-Lowry, or Lewis, which one do we choose? Whatever one, we'll see, here's the thing. If something's an Arrhenius acid, it's probably gonna be a Bronsted-Lowry acid. It's probably gonna be a Lewis acid. So whatever works for you. I think the Bronsted-Lowry definition works the best for me. I'm thinking, okay, can it accept an H+? Can it donate an H+? So, you know, for example, let me think, like if I had some generic acid, H2A, what do you think it's gonna be? It's gonna be a what? It's gonna be an acid. Why is it gonna be an acid? Because there's hydrogens attached to it. It is very likely it will donate protons. So to me, that's a Bronsted-Lowry definition. Or if we had something like, you know, HA minus, if it's a negative charge, it's very likely that this would accept an H+. So that HA minus may behave like a base. So again, it depends on what is easiest for you. Okay, all right, so 12. All right, actually, let's just talk through some of these pH calculations. All right, let's determine the pH of the following solutions. So these two solutions, what's special about them? Oh, let me get my face out of here. I didn't know that was on here. You don't want to see my face. All right, so pH calculations. So we're doing a lot of them. So negative log, so pH equals negative log H+ concentration. POH is negative log OH minus concentration. So what's special about these two substances? They're strong acids and bases, and so we can make an approximation where the analytical concentration of the strong acids and strong bases is what tells me what the H plus or OH minus concentration is at equilibrium for these acid bases. So basically these concentrations basically just go straight into the pH calculation. All right, so the concentration of nitric acid here, because it's a strong acid, you just take negative log. So this is equal to H plus concentration, 0.00457 molarity, and then you just get some number. And so since this molarity has 3 sig figs, our pH needs how many decimal points? 3. So those are the rules for logarithm. So I don't even know what the answer is, but you know, it's whatever that is, all right? So here we have magnesium hydroxide. So we said that this was strong, but it's a strong what? Base. So can I directly calculate pH? No, I want to calculate POH first. So the idea here is, you know, this concentration of magnesium hydroxide is going to be related to my hydroxide concentration. But what's special about this? Yeah, it donates 2 hydroxides because this is, there's 2 anions there. So really the hydroxide concentration, all right, is equal to 0.024 molarity. And that's what goes into my POH calculation, and then I can go ahead and get pH, all right? So basically the strategy for these 2 examples is that they are strong, so they go straight into those pH, POH calculations, all right? I'm not gonna take time and calculate it, but I do want to summarize, you know, how pH, POH are all related. So, you know, if I know my H plus concentration, like I do in my nitric acid example, to get to pH, I take the negative log of that number of H plus. How do I, if I'm given a pH, how do I work myself backwards to H plus? What do I have to do to undo a pH? You do 10 to the negative pH. 10 to the negative pH. That's how you go backwards. All right. All right. So H plus, what if I know H plus? What if I wanted to know the OH minus concentration in a solution? How are those 2 related? How are those 2 related? Or are they related at all? Do you have to be given it? No, if you know the H plus concentration of an aqueous solution, you also know the OH minus concentration. The relationship between these things is Kw equals H plus concentration times OH minus concentration. And at 25 degrees, what is this number always equal to? 1 times 10 to the negative 14, yes. Yes. All right, so that's the relationship to Kw. Kw is the auto-ionization of water. Okay, great. All right, so if we know the OH concentration, how do we get to POH? You take the negative log of it, great. And then to undo it, we do the 10 to the negative POH, great, great. So then how is pH related to POH? Both of them added up equal 14. Why? Why? Because of Kw, yes, this relationship, pH plus POH equals 14, what you essentially did is took the negative log of both sides of the Kw expression. That's what you did, all right? So that means pH plus POH equals 14 is only valid when? At 25 degrees, which is 99.9% of the solutions that we talk about in this class. But if I were to give you like, okay, we have a solution at 50 degrees Celsius, this is the Kw, we would have to return back to these equations to make those relationships between H plus and OH minus. All right, so we could not just do pH plus POH equals 14 at any temperatures other than 25. But you have to usually be given what that Kw is. All right, so with this magic square, all right, see it's a square. If you know one piece, you know it all. You just have to know one corner and you know it all. All right, this is just one tiny facet of this class, but being able to navigate, oh, if I know a pH concentration, I know H plus concentration at equilibrium. I also know OH minus concentration at equilibrium. I also know POH. All of these things are related to one another as long as you have one of those pieces, just one. All right, so just tiny, tiny facet of this class. All right, so that is 11. Okay, so let's do all of these. This is my favorite game. Okay, so we're going to calculate some pHs, or no, we're not. We're going to inspect some weak acids and weak bases. All right, so I have a 0.15 molarity solution of a weak acid, and it has this pH. What is the Ka for this acid? So this was, you know, in chapter 15 and 16, we introduced ice tables. All right, ice stands for what? Initial, change, equilibrium. Yes. Okay. So when doing an ice table, students are always like, well, when do I make an approximation and when do I not? All right. Usually we have to make an approximation when we're trying to calculate the equilibrium line. All right. This question differs from that because this question is asking us to calculate something else. It's asking us to calculate Ka. In this case, it gives us a pH. This is the trick with pHs, all right? Okay, I'm gonna write this down. I'm gonna put it in a big box. You should put it in a big box and you should say this to yourself before you go to sleep tonight. A pH measurement, all right, is an H plus concentration at equilibrium. Or POH, or OH minus, all right? If you are given a pH, that is the H plus concentration at equilibrium. So if you are given a pH, you know the concentration of H plus at equilibrium. So that means you have a piece to the puzzle in the equilibrium line, right? So if you make your ice table, you fill in that pH where it's supposed to go, you should be able to fill in everything else. All right, so let's fill out our ice table. HA, it's an acid. So we need to write out its Ka of it acting as an acid. So HA acting as an acid is HA, equilibrium, H plus, plus A minus. I'm gonna ice table it, all right? Now it's the hard part, putting the pieces in the right place. All right, so 0.15 molarity, where does that go? What line does that go in? Initial, change, or equilibrium? Initial, under what? This one, or this one? The first one, yes. So I start initially with 1.50, right? Do I have any of the other stuff? No, so we're just gonna say 0, 0, cool. All right, which way does this reaction have to go? Has to go to the right, has to go forward. So I love acid-base reactions because the change line is always a 1-to-1-to-1 ratio. So it's minus X plus X plus X. An ice table, it's worked just like a BCA table, but the difference is that the equilibrium line goes into our K expression at the end. So we fill in the equilibrium. So at equilibrium, we have 0.150 minus X. We have X amount of H plus, we have X amount of A minus. All right, so I told you to box and highlight this and go to sleep and say this mantra to yourself. The second thing I want you to go to sleep and say to yourself is that the values in the equilibrium line go into the K expression every single time, whether it is chapter 15, 16, or 17. The equilibrium concentrations always go into K. Always, right? Because K is those are equilibrium concentrations. So whatever is in your equilibrium line, go in to our K expression, okay? So in this case, you know, we're calculating Ka, all right? So Ka, when we formulate Ka, it's always concentration of products over concentration of reactants. So it's H plus times A minus over HA. Cool. All right, so let's keep going. So what's the trick with ice tables? What did I just say? The what line goes into what? The equilibrium line goes into the K expression. So when I rewrite the K expression, it's Ka equals X squared over 0.150 minus X. Great. Well, now what the heck is X? What piece of information did we not use? The pH. Fantastic. So what's the trick with pHs? A pH measurement is H plus concentration at equilibrium. What is the H plus concentration at equilibrium? It is X. It's right there. So X, the concentration of H plus at equilibrium is X. So X, is it 4.29? No, it is 10 to the negative 4.29. All right, so we actually know what X is, yay. So that means we can just plug that value in and solve for Ka, all right? So I'll do that. So that means Ka equals 10, what is 10 to the negative whatever? Do I have it here? Do I have it? 10 to the negative pH is equal to 5.13 times 10 to the negative 5. So when I plug that number into my Ka expression, 5.13 times 10 to the negative 5 squared over 0.150 minus 5.13 times 10 to the negative 5. And then that's Ka, all right? Okay, so let me just back up one little step. You know, this Ka expression probably looks familiar. You've done a ton of Ka expressions that look like this: X squared over initial concentration minus X. What do we often do to the denominator? Neglect X. I did not neglect X here. Why? Why? We're given X. Do not neglect X in this example because we know what X is. The only reason when we neglect X in calculations is why? Why? To avoid the quadratic. So if you neglect X, so someone just write, it's more than 5%. Actually, that's not the right reason. If you neglect X in this question, you're just being lazy. You know what X is. Why don't you just plug it in, right? The whole point of neglecting X is to avoid doing the quadratic. So if you neglect X in this example, yeah, you're just being lazy, all right? Okay, see, that's memorable. You know what it is, just plug it in. Okay, all right, and then there's your answer. Okay, great. All right, yes, yes. Okay, so let's keep going. Okay, so, oh, this looks familiar. 0.15 molarity of a weak base has a pH of blah. What is the Kb of this base? So this question is the exact same. It's the exact same. It's just the only difference, it's not an acid, it's a base, and we're asking for Kb. So we need to write an equation of B acting like a base. So if we start with B, what is a Kb expression? I always remember, in order to make a Kb expression, you have to take the base, you need to add water, and then a base acting like a base is, it's going to, what's the definition of our Bronsted-Lowry base? It blanks a proton, it accepts a proton. So if B steals one of these protons off of a water, you get BH plus, and you're left with hydroxide. So see how there's the product is hydroxide, that's a base, right? And so there's our Kb expression. We see Kb equals BH plus times OH minus over B. Do I put water in the Kb expression? No, it's a liquid. I didn't put states because I'm lazy. There we go, ice table, okay. All right, so we fill in our ice table. It's gonna look exactly the same. Initial 0.15. Okay, nothing over there, minus X, plus X, plus X. We also minus X water, but I don't care about it because it's not going into the K expression. So at equilibrium, 0.15 minus X, we have X amount of BH plus and X amount of OH minus. What's the trick with ice tables? The equilibrium line always goes into K. Yes, but in this case, it's Kb. All right, so KB is equal to x squared over 0.15 minus x. Am I going to neglect that x in this example? No, I'm not. Because what's the trick here? I'm given a pH, so that technically gives me the H plus concentration at equilibrium, but there's no H plus in here. So what am I going to do with that pH? I'm going to convert it to POH and get that OH minus concentration instead. So if the pH is 11.25, the POH is 2.75. Is that right? Is that right? Okay, all right, good. Assuming it's pH plus POH equals 14, it's 25 degrees Celsius. So that means the OH minus concentration at equilibrium, all right, that which is X, it is not 10 to the negative 11.25, it's actually 10 to the negative 2.75. All right, and whatever number that is, I don't know. My key says is this right? Yes, okay, so OH minus concentration at equilibrium equals 0.00178 molarity. There's X. That is my X. And you just plug it in. You just plug it in. And then do we neglect that X on the bottom? No. No. And it's not because it's less than 5%. I don't even know. It's probably not less than 5%. It's because you just don't want to be lazy. Like you just plug it in. Just plug it in. Okay. Good? All right. Okay, let's just talk through this one. Let's talk through this one. Okay, we got again a 0.1 molarity, 1.5 molarity solution of NaA. It has a pH of that. What is the Ka for the acid HA? What the heck? How do we do this one? So hopefully you see the trend. I give you an initial concentration. I give you a pH, which tells you the H plus concentration at equilibrium, but it's asking us for a Ka. The problem is NaA an acid? No, it's not. It's a base. It's a what base? Conjugate base. Yes, it's a weak base. So when I write a chemical equilibrium of NaA in water, I'm not going to write the Ka expression. I'm going to actually write the Kb expression. Yes. So my strategy here is I know NaA is a base. A minus is a base. So I'm going to actually focus on the Kb. I'm going to try to calculate the Kb of that conjugate base first. So A minus plus water gives us HA plus OH minus. This is its Kb expression, all right, of a conjugate base, right? It's no different than me writing B instead of A minus, okay? All right, you still build the Kb expression exactly the same. The Kb expression here is HA over hydroxide over A minus. Do I include water in Kb? No. Okay. So at equilibrium, hopefully you can see everything here. We've done the same calculation over and over. At equilibrium, the concentration of A minus is going to be 0.15 minus X. The concentration of the two products are going to be what? X and X. Great. So that means Kb equals X squared over 0.15 minus X. How do I get X? From the pH, great, but X is equal to what? OH minus concentration. So since X is equal to OH minus concentration, I need to do 10 to the negative POH, not pH. So whatever that is, POH is equal to 4.79. All right, and so, stick that number, get your X value, plug it into Kb then. Am I done once I get Kb? No, what does the question ask for? Ka. Well, I spent all this time calculating Kb. Did I do it for nothing? How do I get Ka? It's from Kw, yes. So understand that Kw equals Ka times Kb. We had to go the Kb route because sodium, NaA, A minus is a base. It's not an acid. We cannot calculate Ka directly. If you try to calculate Ka directly, you will get very confused. Actually, let's try to do that. Let's pretend you wanted to calculate Ka directly, because that's what the question asks for. It asks for what is the Ka of HA. So you might start off with that Ka. You might write HA gives us H plus A minus. All right. You will try to put in the initial line 0.150 molarity into A minus on the product side. You might try to do that. All right. And you'll try to shift to the equilibrium in the left direction. All right. But there's a problem. Do you know how much H plus you have? No. So that's why this ice table doesn't work. So it doesn't work this way. It only works when you start with like an initial concentration in the reactant and then you push it forward. All right. Okay. Yeah. So don't try to do that. There's actually no way you can solve this. All right. Then now you're stuck. Okay. All right. Okay. So let's keep going. So let's calculate some P. So this is these three questions are what I call ice table Sudoku method, where you are given an equilibrium concentration and you have to fill in the rest of the table. All right. You know, with that equilibrium concentration, you know, you do your ice table, you know, you do your minuses, your plus X's and stuff, but you're given a piece of the equilibrium line. You can fill in the rest of the table then. That's what I call the Sudoku method, versus the next 2 pages of calculations. Now I'm asking you, what is the pH of these solutions? So, you know, thinking about these ice tables here, if I'm trying to calculate the pH of a solution, I actually need an equilibrium concentration. I need an OH minus concentration or an H plus concentration. So these questions are inherently different in that we're calculating an equilibrium concentration given Ka. This is where we do the quadratic or make an approximation almost every single time. All right. So in both cases, both of these pages, we do an ice table just a little bit differently. All right. So what is the pH and percent ionization of docwinic acid, HA? The Ka for this acid is 1 times 10 to the negative 5. So docwinic acid is what? An acid or a base? Acid. Yeah, you laugh, but it's going to get harder. Yeah. All right. It's an acid. So what K do you use? Ka. Yes. So let's draw Ka for this. So HA gives us H plus A minus. All right. So what's the concentration? 0.300 molarity. So let's just fill in the ice table. I'll do it once and then we'll do the approximation for the rest. All right. So 0.33 goes in the initial line. We get minus X plus X plus X. For the change line, at equilibrium, we have 0.3 minus X of HA, X of H plus, X of A minus. Does this look familiar? Yes. So Ka, I'm just going to skip this step, is X squared over 0.3 minus X. Did I do something wrong? I don't know. Did I do something wrong? No? Okay, that's fine, Okay. Okay, so how we built the Ka expression is literally exactly the same as the previous questions we did. So Ka equals X squared over initial concentration minus X, but the difference is here, we actually know what Ka is. It's 1 times 10 to the negative 5. All right, so we are trying to calculate for X. We're looking for an equilibrium concentration. So this is inherently harder. Do you want to do the quadratic? No. No. So the nice thing about weak acids and weak bases, they ionize very little. They almost always, you can almost always make an approximation where the amount HA ionizes is really, really small, or the analytical concentration of your acid is really high. So we can just neglect X on the denominator almost every single time. Almost. So this simplifies to X squared over 0.3 equals 1 times 10 to the negative 5. Did I do something wrong? No? You're looking at me like I did something wrong. Okay, all right. You're just confused. Okay. The ice table is exactly the same like we did before. Okay? All right. So when you solve for x, what is x? It is the H plus concentration. How do you know that? Is that something you have to memorize? It's in the ice table, yes. So when you solve for x, you get some number. Crap, what is it? What is it? X is equal to 0.00173 molarity. Okay, and that is equal to the H plus concentration, and then you can get your pH. Okay, why are we all whispering? Why are we all, is this bad? No? This calculation is exactly the same as the previous one. We set up the ice table the exact same. The only difference is we're calculating an equilibrium concentration. Is there some confusion? Yeah. Oh, I didn't get there yet. So we just calculated the pH, that's it. That's it. Yeah, so we just calculated the pH first, okay? Well, actually, I didn't even calculate it yet. So just take that concentration and negative log it. All right, so percent ionization is on your supplemental information packet. Percent ionization is equal to concentration of H plus at equilibrium over the concentration of HA initial times 100. That's it. So it's this number divided by 0.3 times 100. That's it. Okay. All right, so let's keep going. Lisa, it's Dr. N. My TA say they make us do the quadratic. No. I mean, you can do the quadratic, but you can almost always do the approximation, but you just need to know how to do the approximation. All right, so let's do the next one. So what is the pH of a 0.3 molarity sodium dock-winate solution? NaA, the Ka for HA, is 1 times 10 to the negative 5. Okay, so you all laughed at me when I asked you, is dock-winic acid, what is it, an acid or a base? And you laughed at me and you said, it's an acid. What is sodium dock-winate? It's a salt, yes, but specifically, it's a base. It is a conjugate base. Dock-winate is a base. So, should I write Ka? Should I write a Ka expression? No, I should write a Kb because dock-winate is a base. It is A minus. It's essentially A minus. So we got A minus acting as a base. I'm going to draw out Kb. So A minus plus H2O is HA plus OH minus. You just got the joke, yes. I named the acid after myself because an instructor complained about the question. I used pyridine, and they're like, we use pyridine on the exam. Don't use pyridine or whatever. I don't remember what base or acid it was. So I just named them after myself to be more, I don't know. Yeah. Do you get the joke? Yeah. Do you get it? Because, okay, nitric acid is a acid. Nitrate is the anion. It's a salt. It's not the conjugate. It technically is the conjugate base, but it's not a base, all right? Acetic acid is what? It's an acid. Acetate is what? A base. So dock-winic acid is a acid. Dock-winate is a base. Yeah, he sent me an email and then he corrected himself after he wrote it. Okay. All right. Okay, so there we go. So this is the Kb. Okay, so when you do the ice table and you get the equilibrium line, I'm going to skip some steps. All right, A minus, you have 0.3 minus X. You lost some water, but who cares? You gain X amount of HA and you gain X amount of OH minus. So when you draw out KB, what is it? X squared over 0.3 minus X. Do we care about the denominators minus X? No, we don't. So we can make an approximation. Perfect. So are we given KB? No, we're not. So did I do all that work for nothing? No, the difference is here, what piece of information did they give us? Ka. Kb is equal to Kw over Ka. So you just need to make sure that you convert Ka to Kw, or sorry, to Kb first, because A minus is a base. We need to use Kb. All right, and then you solve for X, you get some number. When you solve for X, it is 1.73 times 10 to the negative 5. But what is that concentration? It's the concentration of what? OH minus concentration. How did you know that? The ice table, yes, the ice table. So that is equal to OH minus concentration, and you calculate POH. And then you go one step further to pH. Good? All right. Okay, let's talk through this one. What is the pH of Winonia? I call it B. So what is it? Try again. Read the whole question. So I say, what is the pH of Winonia? B, and I give you the Kb, or yes, the Kb for B is 1 times 10 to the negative 10. So if I give you a Kb for B, B is probably a base. Yes. So Winonia, it's like ammonia. Oh, okay. Again, they complained that I used substances that may show up on the exam. Okay. All right. So if Winonia is a base, what expression do I write? Kb, yes. Do we know what the ice table is going to be already? X squared over 0.3 minus X, but minus X can be neglected. Do I know Kb? Yes, I do. So I don't have to do any Ka, Kw business. I just set that equal to 1 times 10 to the negative 10. When I solve for X, what is X concentration? So what is the answer? It's a 5.48 times 10 to the negative 6 molarity, but it's the concentration of what? OH minus concentration, because it was a Kb expression. All right, and then one more step, you get POH, then you get pH. Okay. All right, so that was Winonia. So then Winonium chloride is what? It is an acid, yes. So ammonia, so remember ammonia, weak bases are inherently harder, all right? So that's NH3, that's my base. Ammonium is NH4 plus, that's BH plus. So if Winonia is a base, Winonium chloride is its conjugate acid, very good. So if it's a conjugate acid, what do I use, Ka or Kb? Ka, why? Because Winonium is a acid. So I use Ka, but I'm not gonna write out the ice table. I hope you can see what we're doing here. Ka is equal to what? X squared over 0.3 minus X, but do you wanna do the quadratic? No. So let's just scribble that out, okay? Equals Ka, but am I given Ka? No, but is that a problem? No, because I can always get Ka from Kw. So it equals Kw over 1 times 10 to the negative 10. Perfect. So when you solve for X, you get something like, you get 0.00548 molarity, but it's the molarity of what? H plus, yes. How do you know that? Because you used Ka and then you get pH. There you go. That's it. All right, perfect. Let's play a game. Let's predict whether these following salts are acidic, basic, or neutral. Right? Because remember, you laughed at me when I said, what is docwinic acid? And you said an acid. Okay, so maybe this will humble you. Okay, so here's some salts. So here's the thing. All right, so acetic acid, HA, right, is what? An acid or a base? An acid, great. When I think about acetate, A minus, so acetic acid is actually CH3COOH, right? That H plus is kind of tacked on the end there. So that's acetic acid, right? When I'm talking about acetate, its conjugate base, it's CH3COO minus. See, that's a base. That's its conjugate base. But the problem is, can you just grab acetate anion off the shelf? Can you type into Amazon Prime acetate anion and buy it? No, that whenever you want a cation or an anion, it has to be attached to something to make it a neutral salt. So you will not find acetate ion on the shelf. What are you actually going to find? You're going to find something like sodium acetate, because sodium acetate is a neutral salt. But the difference is here, so you already said that acetate is a base, but what is sodium? What's sodium? So Na plus. It's a neutral, pH neutral salt. It's a pH neutral cation because it comes from a strong base, right? Okay, so there's the idea that, we can identify weak acids, weak bases, their conjugate forms, but they always have to be attached to something. So we need to dissect both the cation and the anion, determine, okay, is one acidic, is one basic, et cetera, to figure out the overall pH of the salt. And that's what you're gonna do in this lab this week, SAL. Yeah, that's what you're gonna do. All right. So with these salts, I immediately break them up into ions and inspect them differently, or separately. I look at K plus and ClO4 minus. And I ask myself, are these ions acidic, basic, or pH neutral? What is K plus? Neutral. Why is K plus neutral? Because it comes from KOH, which is a strong base. Yes, anything that is the conjugate of a strong base or a strong acid is pH neutral. But anything that's the conjugate of a weak acid or weak base is also a weak acid or weak base. So ClO4 minus, what is that? Yes, it's a conjugate of a strong acid. So ClO4 minus is pH acidic, basic, or neutral? Neutral, yes, because HClO4 is a strong acid. So that would make potassium perchlorate overall pH neutral. All right, so another example would be something that's pH neutral, would be like NaCl. So NaCl is composed of Na plus chloride minus. Na plus is the conjugate of sodium hydroxide, strong base, so Na plus is neutral. Chloride is the conjugate of HCl, a strong acid, again, so that would make chloride pH neutral as well. So NaCl is pH neutral. All right, let's go to harder ones. So NH4NO3, so again, inspect the ions separately, NH4 plus and nitrate minus. So you inspect them separately. NH4 plus is a what? It's a conjugate acid. Yes, so that makes NH4 plus an acid. It is an acid because ammonia, NH3, is a base, a weak base. So NH4 plus is a weak acid. What about nitrate? What is that? That would be neutral, all right? So if you have something neutral plus something acidic, you get something that's Acidic, yes, all right. KCH3COO. K plus is what? Neutral. What about acetate? It's the conjugate base, yeah, so this would be basic because acetate is the conjugate base of acetic acid. So potassium acetate is overall basic. You have the key. All right, iron 3 nitrate. This one's a little bit different. But again, let's just inspect it, one at a time. Iron 3 plus. And nitrate. Nitrate is what? Neutral, so we can ignore it. But what is iron 3 plus? This one's, it doesn't follow, exactly like we were saying before. Iron 3 plus and any highly charged metal cation, these are actually Lewis acids, okay? All right, iron 3 plus, aluminum 3 plus, all of those are Lewis acids. So if I combine a Lewis acid with something that's neutral, what should my pH be? Acidic, yes, so this is acidic, yes. All right, the reason iron 3 plus is a Lewis acid is it's highly charged, all right? So there's, 3 less electrons on it. It doesn't have that many electrons, so it can really only be an electron acceptor, which Lewis acids do. All right, let's keep going. All right, aluminum bromide. So actually this one's the same idea. Aluminum 3 plus is a Lewis acid as well. Br minus is what? That would be neutral because HBr is a strong acid. All right, Ki. K plus is neutral, I minus is neutral, so this is neutral. How do I know I minus is neutral? Hi is a strong acid, yes. Okay, calcium fluoride. Calcium 2 plus is neutral because calcium hydroxide is a strong base, but F minus is a weak base because HF is a weak acid. So that means calcium fluoride is basic. All right, what the heck is that thing? Yeah, so this one is tough. Just squint your eyes and it looks like ammonia. So just change out that methyl group with a hydrogen, all right? So you know how like NH3 and then you have NH4 plus? This is methyl ammonia, where just one of those hydrogens is a methyl group instead. So really this is CH3NH3 plus and chloride minus. So let's do the easy one first. Chloride minus is pH neutral. All right, then what is that? Just squint your eyes. What does it look like? It looks like NH4 plus, doesn't it? So that means that this spinach is what, an acid or a base? It's a weak acid, yes, because methyl ammonia, CH3NH2 is a weak base. Right? Okay. Okay, so let's keep going. All right. So you see in all of these examples, something was neutral? Something was neutral, so we could always ignore something. And so the question is, well, what if one is an acid and one is a base? It's not that bad. We just have to be given Ka values, and then we can understand, which cation or anion are stronger. So, but the process is still, the strategy is still the same here. So let's predict whether this salt, hydrazinium fluoride, is acidic or basic or neutral when dissolved in water. So hydrazinium fluoride. So let's separate it. So fluoride, I know what that is. What is that anion? F minus. So that means the thing that it's attached to has to be what? Plus, yeah, so H2NH3 plus. Does it really matter if we know what it is? you know, like what the structure is? No, not really. We know F minus is what? A acid or a base? It is a base. But what about the other thing? That is probably a weak acid. If you squint your eyes, it looks like ammonia and ammonium. All right. Okay, so for F minus, if that's a base, what should I look up? The Ka value or the Kb value? For F minus. If I want to understand how F minus behaves, do I look up a Ka value or a Kb value? Kb, yes. If I want to know how hydrazinium behaves, do I look up the Ka value or the Kb value? Ka, yeah, because it's an acid. Cool. All right. Wait, but I didn't give you that. I didn't give you that. HF, I give you the Ka for HF, but can we get the Kb for F minus? Yes, through Kw over Ka. So if you just calculate it, I'm just going to do the back of the envelope calculation. This is about 10 to the negative 10. All right. So then the Ka value for hydrazinium comes from the Kb value that's given, which is Kw over Kb, and it's going to be about 10 to the negative 8, about. All right, so that's the Ka, there is the Kb. So these are the values we want to compare. What is stronger, the acid or the base? The acid. So which one wins? The acid wins. So this solution is going to be what? Acidic, yes. Yay. So in this example, both the cation and the anion contributed to the pH. So we have to actually look up the Ka and Kb values, making sure we're actually inspecting the correct one. Yeah. So when you're looking at these ones, oh yeah, yes. The Ka is larger than the Kb. Yes. Yeah. That the acid is acting as a stronger acid. Yeah. Okay. Okay. How do we know it dissociates completely? So all of these examples, A through H and hydrazinium fluoride, these are all salts. And so ionic salts, they all dissociate completely. They're all strong electrolytes. Why is AlBr3 neutral? It's not, it is acidic. AlBr3 is acidic because Al3 plus is a Lewis acid, Br minus is a pH neutral. So if you look at the key, just look at the key. Okay, all right, let's keep going. Oh yeah, let's do this one. All right. How many skincare enthusiasts out there? Yes. All right, so the following structure is glycolic acid, a highly water-soluble alpha hydroxy acid that is popular chemical exfoliant. Which of the indicated protons will ionize more in water? Okay, so let's think about the trends with ionization. When we talk about ionization, specifically with acids, so if we just do HA, H plus A minus, if something ionizes a lot, do you have a lot of product or reactant? Product. So if ionization goes up, how does Ka follow? If you have a lot of product, what should your Ka be? A big number or a small number? Should be a big number, yes. So those are the trends. So ionization typically increases as Ka increases, but we also see that ionization will increase if your concentration of your acid, initial concentration of your acid decreases. Ionization. So what I mean by this is percent ionization, all right? Okay. But we're just focusing on this first trend right here. So essentially, what this question is asking is which hydrogen, which proton is more acidic? Which one is more acidic? So this was a small section in chapter, I don't remember if it was 16 or 17, about the acidity, some of the trends with acidity, with binary acids, with, what was the other one? With oxo acids. So if I have like a hydrogen proton here, what do I want to write? Something like, I don't want to write an M, I'm trying to think of any other letter. Okay, XO with some oxygens attached to it. So some of the trends that we saw is that as the number of oxygen atoms increases, acidity of your proton increases. As the electronegativity of your X atom increases, acidity also increases. So basically, when it comes to acid base and acidity of protons, and again, keep this in your back pocket for organic chemistry, is a proton is more acidic if the conjugate base is stable, right? This process is more likely to happen, all right? It's more, so HA is more likely to dissociate if A minus is really stable. All right, the conjugate base. If the conjugate base is stable, that H plus is more likely to pop off. So this question is asking which hydrogen, which proton is more acidic? Therefore, it's really asking what conjugate base or what thing it's attached to is more stable. All right, so that's the idea here. And so this is a concept, okay? Which hydrogen is more likely to come off? So what I like to do is just scratch off that hydrogen and look at what's left over. So if I remove hydrogen 1, I'm left with a negative charge on that oxygen. If I remove the second hydrogen here, I'm left with a negative charge on that oxygen. Oh, so I just have negative charges on 2 different oxygens. That seems like it's the same type of stability, all right? That we're just putting a negative charge on a fairly electronegative atom, oxygen, but what's the difference between these 2 negative charges? What's special about this location, this negative charge? Resonance, yes. So if this negative charge can undergo resonance, meaning that the negative charge is kind of spread out all along this, this group here. If a negative charge can be spread out, does that make the conjugate base less stable or more stable? More stable. So now can we answer the question, which proton's more acidic, 1 or 2? 2. Great, great. All right, how about, so yes, the answer is 2. How about I reword the question? What if I reword the question? Okay, okay. What if I draw this? O minus C, C. Those are hydrogens. Okay. 1, 2. What if I asked what side is more basic? 1 or 2? What is more basic? Yes, it is 1. Yes, so the side that is more basic is typically the side. Remember how Kas and Kws, Kas and Kbs trend? As Ka increases, Kb for the conjugate decreases. So the crappiest acid is going to be the best base. So in this case, 1 is the best base because site 1 is really unstable, that negative charge is not stabilized. It's those electrons, that negative charge is just going to grab a proton as fast as it can. What is something that grabs protons? Bases. Yes. So spot 2, that negative charge is fairly stable. If it's stable on itself, by itself, does it need a proton? No, it don't need no proton. All right, so it's not going to be a base. All right, because it's stable already. All right, it's an independent weak base. All right, so let's keep going. Oh yeah, let's do this one. I like conceptual things because I don't have to do any math or think about anything. All right, let's consider 2 hypothetical acids, HL and HN. Why'd you think I picked those letters? Yes. Yes. So, and they're the Ka values. So let's just like review these things. Which acid is more acidic, HL or HN? H what? HL, yes. What did we look for? Acidity. We're looking at the Ka value that's bigger, yes. All right, which base is more basic, NaL or NaN? So remember the trends here. As Ka increases, Kb decreases. If we're looking for something that's basic, we're looking for the Kb that's the highest. Therefore, we're actually looking for the Ka that's the lowest. The crappiest acid will be the best base, or the crappiest acid will have a conjugate with the best base. So what is that? NaN. Or you can just calculate it, right? Kb, if Ka is 1 times 10 to the negative 3, Kb is 10 to the negative what? 11? Yeah, remember, Kw equals Ka times Kb. So the exponents have to add up to negative 14. Right, that's why I can do it in my head. I can do that math. So the Kb for Hn, or for N minus, would be what? 10 to the negative 8? Yeah, and so that's what you see. Look, N minus has the larger Kb. Okay, all right. Which solution is more ionized at equilibrium? The 0.1 molarity HL or 0.1 molarity Hn? HL, yes. Because, you know, percent ionization is H plus at equilibrium over initial HA. So essentially this question is asking which one's more acidic, which one has more H plus at equilibrium, essentially, because the initial concentrations are the same. All right, so we know that this ratio differs based upon the Ka value. All right, which solution will have more conjugate base present at equilibrium, HL or Hn? Remember what these are weak acids. So HA gives us H plus plus A minus. So you guys were so fast to say which acid is more acidic. This question is asking the same frickin' thing, okay? Which one has more A minus present at equilibrium? It's asking which one is more ionized. So which one is it? HL, yes, because Ka is bigger. Which has the more stable conjugate base, L minus or N minus? Or which is the more stable conjugate base, L minus or N minus? Here are the numbers. What has good conjugate bases? Strong weak acids, so it's L minus, right? Because it's gonna just give away all of its protons because L minus is so stable. And it's an independent woman. Don't need no protons. All right, which solution is more ionized at equilibrium? 0.1 HL or 0.01 molarity HL? Which one? Yeah, it's the lower concentration one. Yeah, so if we look at percent ionization, all right, the ways we can increase percent ionization, we either increase H plus concentration at equilibrium, so that means Ka. Right? If Ka increases, H plus at equilibrium increases. But another way we can increase percent ionization is actually decrease the denominator. So if you decrease the concentration of the denominator, you get a lot of percent ionization. Yeah, because small numbers in the denominator give you big numbers, yes. Cool. All right. All right, wow, we did all chapter 16. Oh, fudge, we only have like 30 minutes left. Okay, I like to play this game. What's a buffer? Okay, so in all of chapter 16, what we focused on was we either had an acid or we had a base. How a buffer is different, right? Like we either had an acid, we wrote out Ka, or we had a base and we wrote out Kb. But what is a buffer? A buffer is when you have both Ha and A minus present in large quantities. Large quantities. Or you could have your base and your conjugate acid, all right, in large quantities. Very large quantities. And so when we have a buffer, we use the Henderson-Hasselbalch equation, right? pH equals pKa plus log weak base over weak acid, all right? So the way I teach it to my class is that there's two ways to make a buffer. You can either add mole amounts of both HA and A minus just straight into your beaker. Those mole amounts go straight into the Henderson-Hasselbalch equation. There's a second way to make a buffer. You can start with HA and you can partially neutralize it with some strong base, sodium hydroxide. Because when you neutralize a weak acid, you make in situ the conjugate base that you need, all right? And so with method 2, it's a little bit harder because you actually have to account for a neutralization reaction first before you can put it into your Henderson-Hasselbalch equation. So I tell my students that type 2, you have to BCA table first, and then you have to Henderson-Hasselbalch. So we're gonna play a multifaceted game where I ask, is it a buffer or not? And we're gonna figure out, do we plug the number straight into the Henderson-Hasselbalch, or do we have to BCA first and then Henderson-Hasselbalch? So basically I'm gonna ask you, how do we calculate the pH? All right, so A, is that a buffer? So we need to ask ourselves. So remember what we need. We need a acid and its conjugate base, but they have to be part of a weak system. We need a base and its conjugate acid, but they need to be a part of the weak system. So KCl, what is that? That's a salt. What kind of salt? Neutral. Okay, that's a neutral salt. Okay, what's KOH? That's a strong base. So could that ever make a buffer? No, we need something that's weak in there in order for it to be a buffer. So let's say all of these things are in 100 milliliters. If I have 5 millimoles of KCl and 4 millimoles of KOH, how would I calculate the pH of that? What is contributing to the pH? OH minus, yeah. So I have 4 millimoles of OH minus in 100 milliliters. Calculate OH minus concentration, POH, blah, blah, blah. So I essentially ignored KCl. Why can I ignore KCl? Because it's neutral. Okay, great. All right, NaF and sodium hydroxide. Is that a buffer? No. So, but let's walk through it. NaF is what? It's a acid or a base? It's a base. What kind of base? A weak base. Yeah, this question is no different than what we did earlier. Like, is it acidic, basic, or neutral? NaF is a weak base. Yeah, so I have F minus. What is sodium hydroxide? It's a strong base. So I have a weak base and a strong base. Is that a buffer? No, that can't be a buffer. No. Okay, because I need an acid and its conjugate base. So let's play the game. What if we have 5 millimoles of NaF and 4 millimoles of sodium hydroxide? How would I calculate the pH? How would I calculate? And it's all in 100 milliliters. Millimoles. How would I calculate the pH? Yeah, so F minus is a base, but it's a weak base. Sodium hydroxide is a strong base. So which one do we care about more? The strong base. So in this example, actually both of these will have the exact same pH, right? Because we ignore the contribution of the salts in this case, because they're, in KCl it's neutral, but in NaF it's a weak base. Yes, it contributes some OH minus, but not a lot. All right, all of the OH minus is going to come from sodium hydroxide. So it's going to just be, concentration of hydroxide in the system gives you POH, gives you pH. All right, okay. C, is it a buffer? So HCl is a what? Strong acid. What is that? That is a weak base, yes, because I know this, because HClO is a weak acid. So that means its conjugate, its anion has to be a weak base. All right, when you add a base and an acid together, what is that? What happens? You neutralize it, yes. So is this a buffer? Yes, it is a buffer. It is a buffer. Okay, so maybe if I give you some numbers, it'll help you. So, so if I have 3 millimoles of HCl and 8 millimoles of the other thing, and I do my Henderson-Hasselbalch equation, so pH equals pKa plus log base over acid. Pretend I know the pKa already. What's my base to acid ratio that I put into the Henderson-Hasselbalch equation? What do I put in? What's my base to acid ratio? 8/3? No. No. So what is that? Hypochlorite, right, is our weak base. It is our weak base. But HCl, that's a strong acid. So when adding strong acid to this, we actually partially neutralize that weak base first. So we do a neutralization reaction. We got to pull out our 1210 BCA tables first and recognize, oh, when we neutralize some of that weak base, we make the conjugate acid in the beaker itself. So let me actually write out the reaction that's happening. I'm just going to call NaClO, I'm just going to call it NaA because I'm lazy. So when I have NaA and I add HCl, all right, I'm neutralizing A minus. When I neutralize A minus, I'm essentially making HA plus, what else do I get? Sodium chloride. All right, so let's remember our BCA tables. Mole amounts go into the BCA table. So I have 8 millimoles of NaA. I have 3 millimoles of HCl. What's my limiting reactant? HCl, so -3, -3. I have 5 millimoles of NaA left. I have 0 HCl, and I have 3 millimoles of HA. I also have 3 millimoles of NaCl. NaCl, okay, great. All right, so my base to acid ratio in this example is actually going to be 5/3. I have to do a BCA table first because I'm neutralizing it with a strong acid or strong base. I don't care about the NaCl I make in this neutralization reaction because NaCl is what kind of salt? Neutral. Yeah, that's why I'm ignoring it. All right. So this question, so C, yes, is a buffer. It's a type 2 buffer. If you just read my key, you'll see it. You'll see it. D is different. D is also a buffer. Why is D a buffer? HF is an acid, F minus is its conjugate base. So if I have 3 millimoles of HF and 8 millimoles of lithium fluoride, and I plug stuff into the Henderson-Hasselbalch equation, what's my base to acid ratio for D? Now it is 8/3, because remember, it's not any base over any acid. It's the conjugate base over the conjugate acid. So it would be 8/3. For D it would be, but for C, we don't actually have 8 millimoles. We consume 3 millimoles, so there's only 5 millimoles left over 3 of the conjugate acid that we make. So that's why we have to BCA first and C. So what did I say? BCA first, then Henderson-Hasselbalch, but D, you just Henderson-Hasselbalch straight away. All right, HF and KOH, is that a buffer? Yes, it is, because HF is a weak acid, and KOH is a strong base. When you add a strong base to HF, what do you make? What's your product? You make F minus. All right, and so that's a different way we can make a buffer. All right, so let me pick some numbers. What if I have 6 millimoles of HF and 2 millimoles of KOH? What's my base to acid ratio that I put into the Henderson-Hasselbalch equation? Is it 2/6? It's 2/4 because I've partially neutralized some of that HF. I consume 2 millimoles of it. All right, so there's only 4 millimoles left. The only way to make F minus is by adding 2 millimoles of KOH. All right, and in doing that, I consume 2 millimoles of the HA weak acid, so I only have 4 millimoles left. All right, so it's 2/4. All right, KBr and HBr. Is that a buffer? No, because bromide is part of the strong acid system. It is not a weak acid. All right, HCl and HCN. No, those are two acids. Those are two acids. So HCN is a weak acid, but HCl is a strong acid. So yeah, that would not make a buffer. Okay. All right. Oh, geez, there's more. All right. Ammonia and sodium hydroxide. Buffer? Ammonia is what? What kind of base? Weak base. And sodium hydroxide is a strong base. Would that ever make a buffer? No. All right. Ammonia and ammonium chloride. Yes, that is a buffer because we got the weak base and its conjugate acid. Yay. NH3 and HBr. Is that a buffer? So NH3 is a weak base. HBr is a strong acid. What happens when you add a strong acid to a base? You neutralize it and you make NH4+. So is that a buffer? Yes, it is. Okay, so let me make up some numbers. So if I have 7 millimoles of ammonia, and I have 3 millimoles of ammonium, and I do the pH equals pKa plus log base over acid. What's my base over acid ratio for I? What's my weak base and what's my weak acid? How much base do I have? 7 over 3. Yes, because NH3 is a weak base, NH4+ is the weak acid. But what if I have 7 millimoles of ammonia and 3 millimoles of HBr? What is my base to acid ratio here? Yeah, how much base, when these two things react, how much base do I have left? How much weak base do I have left? Yeah, 4. And then how much acid NH4+ did I make? 3, 4 over 3. So these two examples are prime examples of what I call the method 1 to make a buffer. You add the base and its conjugate acid just straight up. It's just all right there. Or the second way to make a buffer is you add like the base or the weak acid, and then you add a strong acid or base to partially neutralize it. So you make the other component in situ, in the test tube itself, or in the beaker itself, right? And that's essentially the basics of a titration, but titrations will not be on this, this exam. Okay. All right, let's keep going. Oh, geez. All right, so there, that is a weak acid, and we add a strong base. Is that a buffer? Yes. This is the same weak acid. HCl is a strong acid. Is that a buffer? No. What is that? That is a weak acid. What is that? That's its base, yes. Well, really, technically, this is the conjugate acid, that's the base, but it doesn't matter, right? They just differ by 1 H+. So that is that a buffer? Yes, it is. Okay, great. Let me add one more. What if I had NH4+ and CH3,3N? That's a base and that's an acid. Is that a buffer? Is that a buffer? But it's a weak acid and a weak base. But it's a weak acid and weak base, but they're not part of the same acid buffer system. They don't share the same pKa or the same Ka. So this would not be a buffer. All right, they're not part of the same thing. Okay, great. All right. Okay, and then like the last part of this chapter, didn't we already do, did we do 23? I don't feel like doing that one. So We can calculate the pHs of all these buffers. So the exercise that we just did was really important in that identifying what is in my beaker, how am I doing the calculation is imperative here. So the question is, what's in my beaker when I put these things together? 100 milliliters of acetic acid and 5 grams of sodium acetate. How do I calculate the pH? So what am I putting in my beaker? So is this method 1 or method 2? Yes, method 1, where we just have straight up, we're adding HA. What is sodium acetate? What's sodium acetate? It's A-. So if we just figure out mole amounts or millimoles amounts of that, then we're free. So they're not reacting. That's the thing. These things aren't reacting, so they go straight into the Henderson-Hasselbalch equation. So given the concentration and volume of acetic acid, how many moles is that? I can't. So 0.02 moles of HA, is that right? Okay, and then of sodium acetate, how do I figure out the mole amounts of sodium acetate? Yeah, I give you gram amounts, so we haven't done one of these in a while, right? And I give you the molar mass, okay? So we can take those 5 grams of sodium acetate, use the molar mass. That 82 goes where, on the top or the bottom? Bottom, good. 82 point whatever grams, 1 mole equals something. Equals something. 0.061 moles of A-. So when I do my pH equation for the Henderson-Hasselbalch, because I have large amounts of HA, I have large amounts of A-. So this is a buffer, Henderson-Hasselbalch equation. So pH equals pKa, so the pKa of acetic acid is 4.74. So I just negative log the Ka value, so 4.74 plus log. What goes on the top? What goes on the bottom? What's going on the top? The base, which is which one? So 0.06 or 0.02 on the top? 0.06, very good. 0.061 over 0.02. And then whatever that is. I'm not going to do the math. All right. 0.3 moles of acetic acid and 0.1 mole of sodium hydroxide in 1 liter. Ka is that. It's a buffer. I'm going to just tell you it's a buffer, but what kind of buffer? Is it a type 1 buffer? Can I just plug those numbers straight into the Henderson-Hasselbalch? Or is it a type 2 buffer where I'm neutralizing it first, then shoving it into the Henderson-Hasselbalch? Type 2, yes. So we have, I don't like red, it's too intense. So HA, I have 0.300 moles of it. And I have, and it's reacting with 0.1 mole of sodium hydroxide, so hydroxide. So what's my limiting reactant here? Hydroxide. So after neutralizing it, I neutralize it to A-. I should only have 0.100 moles of A- after neutralization. All right, so this is after. I'm doing a lazy BCA table. I'm not doing the full one. If you look at the key, you'll see the full one. How much HA do I have left? Do I have 0.3? No, some of it's consumed. So how much is left? 0.2. See how I try to make everything easy, whole numbers? All right. These are the numbers that go into the Henderson-Hasselbalch equation. So when you do pH equals pKa, so it's the same Ka, so 4.74 plus log, what goes on the top? Base, which is which number? The 0.1 over 0.2 equals whatever. Okay, so note how I didn't put 0.1 over 0.3. No, B, it's a type 2 buffer where I partially neutralize it first. Okay. C, we combine acetic acid and sodium hydroxide, but this time it's not mole amounts. I give you milliliters. Yikes. But it's okay, I can just do some quick math to make it the same. So a milliliter times a molarity gives me a millimole, but I'm not very good at math. So what is that? So if you multiply 50 times 0.2, this is 10 millimoles of HA, your acid, acetic acid. And if you multiply 5 milliliters and 0.2 molarity, that is 1 millimole of hydroxide. So these are the two things that we are combining in our BCA table, okay? In our BCA table. So what do we get after our neutralization reaction? What is our limiting reactant? Hydroxide is our limiting reactant. So after this neutralization, how much HA do I have left? 10 millimoles? 9 millimoles, yes. And then how much A minus do I have after the neutralization? 1, okay. So then when I do my base to acid ratio, so 4.74, because it's still acetic acid, log base over acid, it is 1/9. 1/9. Okay, great. Keep going. Gram amounts of pyridine and pyridinium chloride. The Kb of pyridine is blah, molar masses. What kind of buffer is this? Type 1 or type 2? What are we adding into the beaker? The base and the conjugate acid. So this is a type 1. We just need to calculate mole amounts of each and plug it into the Henderson-Hasselbalch equation. But there's a problem here. I give you Kb. The Henderson-Hasselbalch equation we give you guys is Ka. Does that matter? Can I just, take the negative log of that, shove it into the Henderson-Hasselbalch? No, you got to change this. If you take the negative log of this number, you are actually calculating pKb. So in this case, it's 4.74. So that means the pKa of pyridine is actually equal to 9.26. So that's the number you want to put in your Henderson-Hasselbalch equation. So this one, the pKa. Right, that A is there for a reason. So your idea here is just convert pyridine to moles of pyridine and pyridinium chloride to moles of pyridinium chloride, all right? Using the molar masses, I'm not gonna do it, I'll just write the numbers here. 0.06 moles and 0.04 moles. All right, so when I calculate the pH, it's pH equals pKa, so 9.26 plus log 4.3 or whatever, okay? What's the base to acid ratio? What goes on top? What goes on top, guys? Base, yeah, but which number? Which number? Is it 0.4 that goes on top or 0.6? 0.6, yes, because the pyridine is the base. Yes, so it's 0.6 or 0.6 over the 0.04 number. All right, and then that gets you your pH. All right, let's keep going. All right, 40 milliliters of pyridine and 10 milliliters of HCl. What kind of buffer is this? Can I just plug those numbers straight into the Henderson-Hasselbalch? No, you can't. So again, calculating millimoles is really gonna help here. So pyridine is our base. So there is, if you multiply 40 times 0.15, there is 6 millimoles of base. And if you multiply 10 times 0.15, you get 1.5 millimoles of HCl. So that's H+. So after the neutralization reaction, where you have your B and your conjugate acid, how much base do you have? 4.5 millimoles. And then how much conjugate acid did you make in the beaker after adding the strong acid? 1.5. So these are the numbers you put into the Henderson-Hasselbalch. So again, use the same Ka as we had before. I think it's 9.26 plus log base over acid. So what goes on top? 4.5 or 1.5? 4.5 over 1.5. Okay, do not put 6 over 1.5. HCl is not a conjugate acid. It's a strong acid, so you gotta neutralize first. All right, 40 milliliters of pyridinium chloride and some sodium hydroxide. All right, so I think if you multiply this is 6 millimoles, and this is, I think, again, 1.5 millimoles, right? All right, of sodium hydroxide this time. Pyridinium chloride is what? Is it an acid or is it a base? It's an acid. Specifically, it's the conjugate acid of pyridine, so it's BH+. Yeah. Oh, is it? Oh, it is. Yeah, sorry, I was using ammonia. No, just follow the key. I thought this was ammonia. Yes, it's 5, hold on. Yeah, follow the key. So I just did this wrong. What is that? What is that? D. So when you take the negative log of 1.7 times 10 to the negative 9, you get 5. No, okay, wait, hold on. PK, I don't know. Okay, no one's gonna tell me, then I'll just take time and do it myself. 1.7 E negative 9. So the PKB is 8.77, and so then the pKa is just 14 that, so 5.23, yes. So all of this should be 5.23. Okay, 5.23, yes, okay, great, all right. But still, that's honestly not the hardest part. Okay, the hardest part is what numbers to put into the base to acid ratio, because students often, they just think just put any old base and acid into the ratio, whatever base and acid they feel like. But we need to recognize, is a neutralization happening in the beaker before we produce the buffer, or are we just adding mole amounts of buffer? Yeah. For D? For E. What? No, that's a milli. I just forgot the M. Like, yeah, it's just, yeah. Okay. All right. So, what's our base to acid ratio? Is it 6 over 1.5? What is it? What's our base acid ratio going to be? 1.5 over 6? No, 4.5. Because a neutralization is happening first. All right, this one's a little tougher. So we have 40 mils of pyridine and 50 mils of HCl. So let's just get millimole amounts, so it's easier. So what is this? This is 6 millimoles of pyridine. Pyridine is what? A acid, a base. What is it? It's a base, yeah. So I'm just gonna call it B. The giveaway is I give you the KB of pyridine. So KB means base, so I'm gonna just call it B. HCl is a strong acid, so if you multiply those things together, you get, this is 7.5 millimoles of H+. Okay, so remember each time I said, oh, we're doing a neutralization, But when we did this reaction, we did a neutralization. What is the limiting reactant? When we combine 0.5 millimoles of hydroxide and 6 millimoles of BH+. What's the limiting reactant? OH minus, but in this example, what's the limiting reactant? Yeah, the base in this case. So what is in excess after this neutralization reaction? H+. There is 1.5 millimoles of H+ in excess. All right, think about what else is produced in this reaction. You completely neutralize B to its conjugate acid, BH+. It's a weak acid, right? But when you have a strong acid and a weak acid in a mixture, which one do you care about more? The strong acid. So the pH of this solution is just going to be, or I guess the H plus, is going to be 1.5 millimoles of H plus that comes from the strong acid over the total volume. What's the total volume? 90, yep, so 90 milliliters. And so that gives you some concentration. Again, this is coming from the excess HCl in this reaction, this neutralization reaction. What this is actually past your equivalence point. If this was a titration, my class got through titration, so if you're thinking about it, this is after the equivalence point, this is after you completely neutralized your base, and so all that is extra floating around in there is extra strong acid, right? And so whatever this calculation is will give you your pH. Okay, so it's just the H plus. We don't care about that BH plus. We did examples like that where we just ignored the weak component. We're just kind of putting it all together. I'm not explicitly telling you, what component to focus on. All right, there's two more, so I'll just finish here. All right. Okay, so 50 mils of sodium acetate, 20 mils of HCl. So if we calculate millimole amounts of this, there is 10 millimoles of sodium acetate. What is that? That's a base. So I'm gonna just call it A minus because it's the conjugate base of a weak acid. And then HCl is our strong acid. How many millimoles is that? 4 millimoles of H plus. Okay, so in this example, what's limiting? The acid. So after your BCA table, how much A minus do you have left? 6 millimoles. How much HA did you make from the neutralization? 4. So these are the numbers that go into your Henderson-Hasselbalch equation. Your base to acid ratio, when you do this, because the Ka of acetic acid is 4.74, is something like, what is it, 6 over 4 or 4 over 6? 6 over 4, yes. It is not 10 over 4 because a neutralization reaction is happening. Okay, we'll do the last one and then we'll be done. HCl and sodium hydroxide. Is that a buffer? No, that's not a buffer. So it doesn't have a pH then, right? No, that's not true. We can still calculate the pH because let's think about it. An acid-base neutralization reaction. You have HCl, that's an acid. You have sodium hydroxide, that's a base. Well, what products do you make? NaCl and water. So let's look at the products. Does NaCl contribute any pH? No. If this was earlier in the chapter and I asked you, is NaCl acidic, basic, or neutral? You would say neutral. Does water contribute pH? No. So what I'm actually looking for here is, okay, which one of these species is in excess? Whatever species is in excess is what's going to dictate my final pH, because all my products are just neutral. So if I figure out the millimole amounts of these two species, all right, so 40, well, actually just looking at it, can you tell which one's in excess? Sodium hydroxide, the acid or the base? The base, yeah, because there's more volume, but let's just check it. There's 10 millimoles of H plus and 11.25 millimoles of OH minus. So now you can see clearly that hydroxide is in excess. So how much is left over after this neutralization reaction of hydroxide? 1.25 millimoles. Great, so I just shove that into negative log POH, get pH. I just put negative log 1.25, that's my pH. No, how do I get hydroxide concentration of the final mixture? I have to divide by volume. Do I divide by 45? No, I divide by 85. Yeah, so 85 milliliters will get me my concentration, whatever that is, and then you calculate POH, and then you calculate pH. All right, we'll be done. Okay. Thanks, guys. Do remember that there's the key, like the link to the key is on the top of the page of the handout, so you can just look through my key.